In this video, we're going to go ahead and set the stage for L'Hopital's rule, talk about what we're going to learn in this whole lesson, and then do the warm-up. All right, so L'Hopital's rule. Remember at the beginning of this class, we were interested in finding the slope of the tangent line. Said another way, we were interested in finding instantaneous rates of change. And we didn't have a methodology for this yet. We had to estimate those instantaneous rates of change, estimate those derivatives by calculating slopes of secant lines over smaller and smaller intervals. And then we were saying, you know what, this is really inefficient. We need to formalize what we mean by rise over run as run goes to zero. We need to formalize the idea of a limit. How close is close enough? Now that we have derivatives, though, we're going to apply our knowledge of derivatives to evaluate limits. We're going to evaluate limits of two different forms. Remember, if you just plug in with your direct substitution and you get away with it, you've evaluated that limit because that function was continuous at that point. But if you plug in and you get a 0 in the numerator and a 0 in the denominator, there's work that needs to be done. Or similarly, if you plug in and the numerator is getting really, really big, say really big and positive, and the denominator is also getting really big, say really big and positive, there's work to be done here to analyze that, okay? And so in this packet, we are going to be identifying those forms and then applying L'Hopital's rules to evaluate those limits. In the past, we were able to evaluate indeterminate forms of 0 over 0 or infinity over infinity, but they were very special cases. And let's look at, remind ourselves what those techniques were. Okay. So remember what the limit notation is always asking you. It's saying as whatever is happening down there, as x goes to positive 4, what does this function, what is y equals x squared minus 16 all over x minus 4, where do those y values, those function values go? Right, so that's the question. As x is going to 4, what is x squared minus 16 over x minus 4 going to? Okay. Now, notice if we do we try direct substitution, we run into some challenges here. So I'm just attempting 4 squared minus 16 all over 4, scooch this down a little bit, all over 4 minus 4. Uh-oh, this is 0 over 0. We don't know anything. Right? If you plug in and you get undefined, you're just saying that 4 is not in the domain of this function. So there's work to be done here, and the work is to go ahead and factor, and I'm hopeful that we've got a whole here. So if I factor that numerator, x minus 4 times x plus 4, all over the denominator, x minus 4, the technique, and I do want to talk about why this works again. We did that a lot at the beginning of the semester, but the technique is to remove this whole, remove that domain restriction. I don't care about the domain restriction to evaluate the limit. I now have a new function, x plus 4, and that function is perfectly continuous at x equals 4. So now when I'm getting to do this direct substitution, I'm plugging in the 4 for that x. We get 4 plus 4. We've evaluated the limit. 8. What claim have we actually done? Well, the graph of y equals x squared minus 16 all over x minus 4 looks exactly like the graph of y equals x plus 4, but it has an added domain restriction, x can't be 4. So it just has a little hole there. I'm going to make a quick sketch. All right, so right here, this line with a little hole at 4, 8, that's your function y equals x squared minus 16 all over x minus 4. X values near 4 are mapping to y values near 8, which is why 8 is our limit, right? So algebraically, what we're doing is we're factoring, we're acknowledging that hole. I don't care about the hole to evaluate the limit, so I remove the hole. In other words, I plug in this function, I fill in that hole, and then I can evaluate this limit through direct substitution, right? Now let's investigate this one over here. The limit as x approaches infinity of 4x squared plus 5x all over 1 minus 3x squared. Now, remember that what dominates here is those highest powers of x. So I'm going to go ahead and write it in descending order. That 3 is negative, minus 3x squared plus a 1. And we learned that when the degree of the numerator and the degree of the denominator were the same, that there was a tie, and the answer is actually just sitting here. It's that ratio of the leading coefficients, 4 over minus 3. In other words, minus 4/3. Right? Notice though, that if we do put in a big number for x, a big number squared times 4 is a really, really big number. This doesn't really dominate for huge powers of x. So the numerator is going off to positive infinity. The denominator is going to minus infinity, right? A huge number squared is a huge positive number times minus 3 is negative. If I did that sort of analysis, we have infinity over minus infinity. There are a lot of options. Either the numerator dominates and this blows up to positive infinity, or the denominator dominates and this goes down to 0. You have that horizontal asymptote being the x-axis, or there's a tiebreaker. The relative sizes of those infinities are the same, and that's the case that we have here. And again, we were able to identify that quickly by seeing the degrees of these numerators being the same. We made an algebraic argument for this, though. Let's just review that for fun. Limit as x goes to infinity of 4x squared plus 5x all over minus 3x squared plus 1. We multiplied by 1 in the form of 1 all over the highest power of x in the denominator, and then something over itself is a big fancy 1. Multiplying fractions straight across, we have 4x squared, and distributing this all over x squared, plus 5x all over x squared. That's my numerator. My denominator is a minus 3x squared all over x squared plus 1 all over x squared. All right. Simplifying here, we've got 4 plus 5 over x all over a minus 3 plus 1 over x squared. Now each of these are on their way to 0 as x is getting really, really big, right? 5 over huge, there's $5 in the US, you all get to share it. What do you get? Essentially nothing. 1 over huge squared, 1 over huge is also on its way to 0. So that's why what's left over here is the limit of that constant, which is just the constant. Minus 4/3 done as our answer. right? So here are two examples of some indeterminate forms, and we had these algebraic techniques. One was factoring, seeing that we have a hole, filling in that hole and evaluating the limit through continuity. The other was really, if you look up end behavior, we have all this in our previous notes of rational functions. I'm just going to write rationals. We had this fancy, clever multiplying by 1 to see what features dominated as x got big and positive. Now, what if these fail? What if we have an indeterminate form like 0 over 0 or infinity over infinity, and we don't have a technique like this? What can we do? That's what motivates L'Hopital's rule. All right, so the video is over, but I'm having a technical difficulty here where it's not allowing me to save, so don't watch past this.